So in this lecture video, I want to talk about electric fields inside conductors. So for starters, I want to define what a conductor is. So it's basically a material that has mobile charges inside it that can move freely within the volume and the surface of the material. And in doing so, it can create regions locally that have maybe a little more positive or a little more negative charge. Okay, so these, so your typical conductors are materials that you're very familiar with, metals like copper, aluminum, steel, things like that. Okay, and so in general, and we'll talk about this in a couple lectures, they're able to conduct electricity. And so in these conductors, in fact, there are many protons and many electrons inside. Some small fraction of the electrons, you might have learned this in chemistry, some small fraction of the electrons are highly mobile, so they can kind of move throughout the material. The majority of the electrons are actually pinned very close to the atomic nucleus, and they're not able to travel very far. But there is still a large number of electrons, even that small fraction, because there's on the order of about 10 to the 22 or 10 to the 21 electrons in sort of a chunk of material that you might pick up. So they're still on the order of a fraction, sort of on the order of about 1% of the electrons are able to move very freely, and in doing so, they're able to sort of locally polarize the material. So there may be areas that have a little more plus charge, areas that have a little more negative charge. All right. So one thing to keep in mind is that even though in the material only the negative charges are able to move, because the protons and the nuclei themselves are kind of locked into the crystal lattice, that you can still generate regions that have more positive charge, and that's just a region where there's less electrons. So if you can imagine, in a material, in general, you might overall the material has the same number of positive charge as negative charge, but you can imagine regions where the electrons there's a little bit fewer electrons, so on the whole there's a little more protons, which means somewhere else in the material there's regions where there's a little more, a few more electrons, so that area has a little more negative charge. Okay, so that's basically in a nutshell what a conductor is. And so what I'm going to talk about today is how we deal with these conductors when we place them in electric fields, right? And this is very useful. So, when we think about modern telecommunications and everything, we deal with, everything that we work with is usually made out of metal. Our antennas are made out of metal. And we need to know how electric fields interact with conductors. So basically in electrostatics, which is what we're dealing with right now, we're going to demand one thing, and that's written down here, which is we're going to require that there are no moving charges inside the conductor, okay? And that's basically just the definition of electrostatics, right? So static means there's nothing moving inside. In about a week, we'll talk about the case when actually there are electric fields inside conductors. Like, so for instance, if you hook one end of a conductor to a battery, opposite ends of a conductor to a battery, then you're going to be passing a current through it. Okay, so that is not electrostatics, because by definition you're pumping a current through it, and you're forcing charges to move in it. Okay, we're not talking about that today. So we're talking about electrostatics, and in this case we're going to demand that there are no moving charges inside. Okay, so this one requirement actually implies a lot of things about electric fields inside conductors. So for starters, number one, basically, if there are no moving charges inside the conductor, that means there must be no fields inside the conductor. I'm just going to write that now. So as I've written here, that implies there are no electric fields E inside a conductor. And we can think of basically what happens if there is an electric field inside, right? So if I look at this, so this blue blob that I've drawn here is supposed to represent a conductor. Let's imagine there's, like I said, billions and billions of electrons inside. So let's look at one electron over here. Let's imagine there was an electric field inside the conductor, right? So let's say there was an electric field pointing out this way or whichever direction. So if there was an electric field here, then the electron would experience a force. Since the electron is negatively charged, it will experience a force that way, which will cause it to accelerate and move in that direction, right? And that basically goes against this original requirement that there are no moving charges inside the conductor. So basically we know that this condition has to be false, and the only way you can have that is to have no fields inside, right? So if there were fields inside the conductor, there would be moving charges. All right, so the second thing is that if there are no electric fields inside the conductor, what that means is then that every point inside the conductor must be in equipotential, okay? And we talked about equipotential in the last lecture. I'm just going to write this now. All right, so you can see that, you know, if there is no field inside, right, and we consider the amount of work it takes to go from some point A, you know, let's say to some point B, let's say B was on the surface, right, the amount of the voltage from B to A is just minus E dot dl. And since there is no electric field inside, this is always 0, right? And that's true, you know, if I wanted to go to some other point on the surface as well, right? So the every point inside the conductor, every point on the surface is an equipotential. So that's implication 2 that we get directly from the fact that there are no moving charges inside the conductor. All right. I'm just going to erase this here. So I'm going to do a little more drawing. So implication 3 is that if the surface, you know, we just said now that the entire volume, and in fact the surface, is an equipotential. So if the surface is an equipotential, then what that means is, from what we learned about equipotentials in the last lecture video, the electric field then must be perpendicular everywhere on the surface, right? That's what we learned about equipotentials, is that the electric field is always perpendicular to the equipotential. If the surface of the conductor is an equipotential, then that implies that the electric field must be perpendicular everywhere. So let me just write that down. So, you know, let's imagine, for instance, a case where the electric field wasn't perpendicular everywhere on the surface, right? So so I've drawn this electric field over here. It's pointing in kind of diagonally from the surface. So of course you can decompose that vector into a component that's going to be perpendicular to the surface. It's supposed to be perpendicular. And a vector that's going to be parallel to the surface, right? So this is E perp. This is E parallel. As I'll show in a second, you can have charges on the surface, so that can cancel out the E perpendicular component, but you can see that because locally this looks kind of flat, the electric field should be pointing out, that the charges on the surface won't generate an E parallel component. So if there is an E parallel component somewhere on the surface, then that will cause, you know, if I put a charge here, right, that will cause that charge, that electron, to accelerate. If the electron's negatively charged, it'll accelerate in the opposite direction, but it'll cause the charges to move along the surface, right? And that violates our requirement. So if the electric field was not perpendicular everywhere on the surface, we would have moving charges along the surface, which violate our original requirement. So obviously the electric field has to then be perpendicular everywhere on the surface for the system to be in electrostatic equilibrium. Okay, so I'm just going to erase this. And then sort of the last implication is I think quite straightforward. So number 4 says if we have no electric fields inside the conductor, that must also mean there are no net charges inside the conductor. So I'll write that down. So, as I said, if you look inside a conductor, in fact, there are, billions of charges inside, but inside the bulk of a conductor, every region has basically equal numbers of negative and positive charges. So the net amount of charge inside the sort of bulk of a conductor should be 0. You can, in fact, if you put net charges on a conductor, they will basically exist on the surfaces of the conductor. Either an inner surface, as I'll talk about later, or in this case, this is a closed conductor, so it just has an outer surface. So how can we prove number 4? Well, we can just see that using Gauss's law, right? So let's imagine I'm just going to take some region inside of this conductor, and we just said that the electric field is 0 everywhere inside the conductor. So what that means then, if the electric field is 0 everywhere inside the conductor, then basically the flux E has to be equal to 0, because E is 0, which means that Q enclosed has to be 0, right? By Gauss's law. And I can shrink this Gaussian surface. I can make a Gaussian surface anywhere, and I can shrink it to however small I want. And basically, this is always, since there is no electric field everywhere, the net Q enclosed at every single point in this conductor has to be 0. All right. So what this is going to look like then is if you imagine then I'm going to bring some positive charge, let's imagine I have a point charge out here, right? So what the electric field is going to look like from this point charge will be something like this, right? So if we're demanding that the electric field, so if A, there's going to be no field inside the conductor, so close to the point charge, it'll look just like a point charge like a field distribution. But then when you get close to the surface of the conductor, it's going to warp a little bit. I'm not going to draw all the field lines. I've tried to do my best to show that the field lines come in perpendicular, okay, to the surface. And they're going to terminate at the surface. If they're going to terminate at the surface, we know that the only thing that really can kill a field line will be a negative charge. So I'm going to draw some negative charges. So on the bottom part of this conductor, we're going to have some excess negative charges. These negative charges may not be distributed uniformly along the surface. They will be only on the surface, not in the bulk. But they'll be distributed in a way to make sure you cancel the electric field inside the conductor. And in fact, if we look at, let's say, the back side of the conductor, so we have, let's start off by saying this conductor is neutral, so there's no net charge. So there's excess negative charge here. There has to be some positive charge. Use a different color. There has to be some excess positive charge somewhere else, so we're going to put it here on this side. All right, and there'll be some spread out along the sides too, but I'm just not going to draw all those. So, we know that when we get very, very far away from this, we'll still see some kind of electric field from a point charge, but so you'll see something that, may look like there'll be some positive field lines then coming out like this, right? And so what happens is basically and they're all going to be perpendicular to the surface. So what's going to happen is that you have some negative charges, on this surface. You have some positive charges here. You have a point charge here. The superposition of this point charge, these negative charges, these positive charges here will basically conspire to make sure that every point inside the conductor, the field will be 0. And the way it does that is basically the charges here, there are billions and billions of charges. They can move very, very quickly. We're not going to worry about, how quickly they move in this problem. They can redistribute themselves in fractions of a nanosecond. And they configure themselves so that they can make sure that there is no net field inside the conductor. So it's sort of like a self-organizational thing where the electrons basically redistribute themselves and do so in such a way to make sure there is no net field inside. So I just want to spend a couple minutes describing how the conductor actually sort of achieves this state where there's no field inside. Okay? So let's imagine that we have a situation where we have some object, it's this egg-shaped object, and it's some material where there are absolutely no mobile charges inside. So somehow you've been able to, freeze the charges so they basically can't move. We learned even, with the situation of the foam chips, like if you have an insulator, the charges can move a little bit, so the electrons can displace slightly off the nucleus. Let's just ignore that for this time being. So let's imagine this thing just cannot, there's no mobile charges, the electrons can't even polarize, and I just apply some constant electric field, right? So if I have no mobile charges, the electric field is just going to go right through this object, right? So there's just going to be some constant electric field inside. So now let's imagine the case in which there are mobile charges. Okay, so allow charges to move. And, so imagine it's the same material, but somehow you've just, snapped your fingers and you've now allowed the charges to kind of move around freely inside the material. And we'll say that this material has no net charge initially, right? So it's a neutral chunk of material. All right, so I'm going to drop blue now just to signify that it's a conductor. All right, and so what's going to happen, and I'll start with this drawing over here. So, you have charges inside. The charges then will be accelerated. So for instance, if you had an electron here, and, I'm basically talking about the process by which the conductor makes sure there is no field inside. So let's imagine, you unfroze all the electrons, and now I have an electron here that it sees an electric field, so it's going to be accelerated in the opposite direction towards here. So basically, if I have electrons in the material, a lot of them are going to be accelerated towards this side, right? So what's going to happen is when I let the electrons move, a lot of the electrons will accumulate onto this side of the conductor, leaving more positive stuff on this side, right? And this happens very quickly. So this electrons move, at the order of about, about 100,000 meters per second in a typical material. It depends on something called the Fermi velocity. That's a little bit beyond the scope of this course, but they move very, very fast. So, for the purposes of this course, you can think of them think of them as moving almost instantaneously. So they basically move to this side, and they will, it's the electric field line. So, the electric field before was constant, but now there's some negative charge here. And it's going to, the electrons will basically continue to move around, actually, until, if there is some electric field that's left in here, right, that will cause the charge to move. That will set up, that will basically, that move charge will then change the electric field inside. And what will happen is that the charges here will kind of do a little dance, and they'll keep on accelerating. If there is any electric field left in here, the charges will keep moving, and eventually what will happen is that they'll reach some configuration where there is no electric field left inside, so the charges can no longer move, and that's basically the configuration in which we sort of consider in electrostatics. But this dance is so quick because the electrons move so fast that this whole process takes, like I said, typically on the order of about 10 to the minus 12 seconds, picoseconds. So You just don't need to worry about it for the purposes of this class. You can just think of it as instantaneously rearranging themselves. So another important thing to remember is that when the electrons rearrange themselves on the surface charge density is in general non-uniform, okay, for an arbitrarily shaped object. If you have something like a sphere, then it could be uniform, depending on what the external electric field is. But the surface charge density for the conductor, unless you have a highly symmetric situation, is generally non-uniform. And it's non-uniform in such a way to completely cancel out the electric field inside. But E inside is 0. Okay. And again, no net charge inside. All right, so now what I want to talk about is what happens when you put some, so these last examples have been for a neutral conductor, right? So it's a conductor that doesn't have any net charge on it. Now I want to just briefly talk about what happens, you know, again, if we have some chunk of material and I'm going to put some net charge on it, right? So let's imagine I have some block of conductor, and I'm going to, you know, use a plexiglass rod that I've charged up, and I'm gonna, you know, touch the conductor with that a bunch of times, and so I'm going to put some excess electric charge on it. So what happens, right? So, oops, that's a pretty fat pen. So basically, you just follow exactly the same rules as we did for the neutral conductor. So first of all, there is going to be no net charge inside the conductor, which basically implies that the net charge has to go onto the outside of the conductor. So let me write all this down. So as I just said, the net charge exists only on the surface of the conductor. Because of that fact, you can also say, and you know, just due to the fact that if we had a charge in here, because it's this is electrostatics, you know, that any little charge in here would not be moving. So that means that the electric field inside the conductor is still 0. That's no different than for the neutral conductor. And so there is no net charge inside. That's basically the same statement as number 1. No net charge inside the bulk of the conductor. And again, you know, you can use that Gauss's law argument, right? So if there's no electric field inside, you can define some little Gaussian surface. The flux through it has to be 0 no matter how big or where it is. If the flux through it is 0, there's no net charge inside. And again, you know, if I put some charge onto the surface here, it is not necessarily going to be arranged uniformly, right? So if this was a perfect sphere, and we learned about this for this, you know, for a shell of charge, if this was a perfect sphere, then yes, the charges would arrange themselves uniformly. But if it's just some funny shaped object, the charges on the surface have to arrange themselves in such a way to make sure the electric field at every point is equal to 0. So there is some unique configuration by which that can be accomplished, but it doesn't necessarily have to be uniform. So again, the surface charge density in this case does not have to be uniform. Surface. I'll just pause. So again, the electric fields that are generated by some, you know, so let's just say I've put a net charge, you know, plus Q onto the conductor. So I'll just write that down. So net charge plus Q. So the electric field at the surface of the conductor, again, will be just perpendicular to the surface at every point. Something like this, right? So it won't necessarily look like a point charge at all, depending on, at least locally, close to the surface, depending on what the shape of the conductor is. All right, that's enough. And so we can ask what is the strength of the electric field at some point. So it's kind of hard to define, the strength of the electric field. It could be different at different points of the conductor, because the charge density might be different at different points. But let's imagine we're going to look at one specific point, okay? So let's select, I don't know, just some arbitrary point. So let's look over here. So I'm going to blow that up. So if we wanted to know the charge density at that point, or sorry, the electric field at that point. So let's say that, so this is the surface of the conductor there, and we've got some charge density there. So I'll call this, local charge density sigma. And again, sigma can be different everywhere on the surface, okay? So if I look just very close to the surface, this does not work if I try to get far away from the object. But if I look very, very, very close to the surface, this, even this small patch looks kind of, you can kind of imagine this is sort of like an infinite sheet, right? But only when you're very close to the surface. So just, locally, the electric field is going to be coming out perpendicular, right? And it's going to vary everywhere on the surface. So I can't, go to large length scales. But if I'm just sort of, a fraction of a micron away from the surface, and I just want to know what the electric field is just right up at the surface, I can kind of do the same thing I would do for the infinite sheet in Gauss's law, right? So I can make some kind of Gaussian surface. So I'll choose like a cylindrical surface like this. And then I can ask how much electric field is, the electric field here is coming out perpendicular to the surface. And I'm, when I get far enough away, these field lines are going to start to move around and not be exactly perpendicular. But like I said, this is just very, very close to the surface of the conductor. I can basically define so locally, the conductor looks like an infinite flat sheet. Of density, of surface density sigma. Okay, sigma can vary over the sheet. But in this little patch here, because we're making this patch be very small, well, let me just rewrite this. Sigma, I'll just erase that. So sigma right around this patch you can treat as constant, okay? But then, when you get sufficiently far away, and this is just because this little Gaussian surface is microscopic, okay? So at a microscopic level, you can treat this as being perfectly perpendicular. You can treat the charge density as effectively uniform, okay? So sigma here is approximately uniform. Okay, so now we're just doing a Gauss's law problem. So then we know that Q enclosed in Gauss's law over epsilon naught is going to be equal to, whatever the surface area of this little box is. So that's going to be sigma, which we're treating as approximately constant, divided by the cross-sectional area of this circle here. or whatever shape you've picked, over epsilon naught. And that's going to be equal to the integral of the flux over that closed surface, E dot dA. Right? And so we're going to treat the electric field here as being effectively constant because we're making this pillbox sort of, just fractions of a millimeter. So they're very, very close to the surface, microns. And so basically we're going to treat the electric field as effectively constant. So for the top surface, it's going to just be E times A. Right? For the bottom surface, there's actually no electric field, right? We said there is no electric field inside the conductor. The bottom surface is inside the conductor, so this is 0, right? This comes from no field inside conductors. So then what we get is just, sigma A over epsilon naught is E times A. So A's cancel. So the electric field just directly above some little patch of a conductor is just sigma divided by epsilon naught. Okay, so that's the magnitude of the electric field directly above a conductor. But that's just locally. That's just because, again, sigma may be different everywhere on the conductor. So here it might be, I don't know, 1 volt per meter. Here it might be 2 volts per meter because maybe the charge density is twice as big here. Okay, so I'll just write that down. So the last thing I want to mention very briefly is just that what happens if, for instance, I have a hole inside the conductor, right? So imagine if I have a conductor here, and we'll go through this in lecture, and there was like a little hollow drilled inside, okay? And there's a little hollow, I could put another charge in there. So what I want to basically just say very quickly is that, let's imagine I put a positive charge in here. There can be an electric field inside the hollow region. Okay, in principle, if I put a charge in here, there can be some electric field inside. All right. But so when I say there is no electric field inside the conductor, it means in the region of, where there's actually the material of the conductor. If I've drilled a hole in here, then there can be in principle an electric field inside this hole. So all these rules apply to, where there's actually the material of the conductor. If I've emptied out some part of the conductor, we can have a net charge in there. We can have an electric field in there. It just, but then you have to then treat this surface of the conductor much like you would treat the outer surface. So the rules about the surface of the conductor also apply to the inner surfaces. But, if I have a little net charge in here, then what that means is that there has to be then some negative charge built up on the inside wall here to balance out the electric field, to cancel out the electric field from that little positive charge I've put in there. All right, so that's it for today.